because what I said, I think I said last time that some of this stuff, the most efficient thing you can do is use these formulas often enough until you remember them, okay? Now, come on. That's what I'm looking for. If you can't remember the derivative of the sine and the derivative of the cosine, you can derive them. It just takes a little bit of time. And really what it takes is thought. It's not even a lot of calculations. So here's what the sine looks like. The sine curve starts at the origin at 0. It rises up, it falls back, and like this, right? So at 0, this is pi over 2. This is pi, 3 pi over 2, and then 2 pi. That's what the sine looks like. Okay? And this is generally a value of 1, and this is minus 1. So remember what the definition of a derivative is. It's the slope of the tangent line of the curve. So if this is the sine curve, the derivative of the sine is a curve based on the slope of this. Okay? So let me come over here and draw another graph. So this is the sine. This is the derivative of the sine. And with respect to x. This is the x curve, x-axis. What do we know about derivatives right here? Now go ahead and say it. I think you were right. It's zero.
Okay.
It's 0 because the derivative is the slope. And what is the slope of a line tangent to this point? 0. And we know down here the derivative is 0 as well. Right? So 0, pi over 2, pi, 3 pi over 2, and then 2 pi. At pi over 2 and 3 pi over 2, the slope of the sine is 0. Okay, so we have 2 points. At 0, the slope of this curve, it's positive, and it's very large. It's a very steeply sloped curve. So at 0, the slope is a very large number. And it goes from a large number to 0. And the slope gets gradually closer to 0. It's not a straight line to 0 because it has this curvature. So we can show that the slope looks something like that. And from pi over 2 to pi, the slope is negative. And it goes from a 0 value to a very steep negative value. And then if you keep going, it returns to 0. It's a very negative slope. From pi over 2 to 3 pi over 2, it's a negative slope. From pi over 2 to pi, it gets more and more negative, steeper and steeper, until it hits its lowest value. And then from pi to 3 pi over 2, it gets less and less negative until it returns to 0. So from pi over 2, pi over 2 at 0, it gets more and more negative until it reaches pi, at which point it gets less and less negative until it reaches 3 pi over 2 when it returns to 0. And from 3 pi over 2 to 2 pi, it's a positive slope again. And it gets its steepest point right here. So you can have a seat. It gets positive until it reaches its maximum up there. So again, the derivative of any function is simply the slope of the tangent line for that function. And you determine the slope at various points along that function and then connect them. And if you look at this curve, if you remember your trigonometry, that's what a cosine curve looks like. So that's how you can derive the sine. But again, you really have to sit and think about this. Like, you know, is this a positive slope or a negative slope? Here it's 0. This is positive, so this is a very high number. The slope is 0 here. This is a negative slope. It's getting more and more negative until it reaches a minimum, its lowest slope, and then it gets less and less negative until it reaches 0. So you can think about this and figure it out. It just takes a long time. And this is why, in my view, things like this, for derivatives of sines and cosines and things like that, the product or the product rule, et cetera, the ones that are in the back of your book, it's most efficient if you go through the homework, do that homework over and over and over again so that it sticks in your head. So after going through all of this, does that answer your question? Okay. All right. And this reminds me, if we can shut our phones off, because we don't need to be interrupted by messages and phone calls for the next couple of hours. All right. So, any other questions? This is what we were doing last time. We took some derivatives, and we showed, again, that the derivative of position is slope. The change in position with respect to distance is slope. The change in the slope with respect to distance is the moment, and that's the second derivative of position. The change in the moment with respect to x is the shear force, and that's the third derivative of position. The change in shear force with position is the distributed load, and that's the fourth derivative. So in mechanics of materials, we can go through these various derivatives. This process can be applied to almost any field, and you'll have different parameter names for the various derivatives, but you can take as many derivatives as you need. First, second, third, fourth, eighth, 10th, 20th derivative. And these are on Blackboard, so if you don't write down everything that's on the slide, you can go back and take a look at them on Blackboard. So we went through this example, and I wanted to highlight this because he's not here now, but somebody had asked about this equation. If we take, and we went through, we determined the first derivative, which was the slope. That was the answer to this question. You can take the second derivative to get the moment. The third derivative gives you the shear force. And if you take the fourth derivative, which is the distributed load, in this case, the fourth derivative was 0, which kind of makes sense because the problem had a point load. There is no distributed load. And so one of the things I wanted to highlight was that it's important to use your intuition to at least make a guess as to whether or not your answer is right. If you know it's got a point load, by definition it's not a distributed load, and you come up with a fourth derivative that has some function in it of load with respect to x, has the load changes as it goes, as you move across that beam, that should tell you there's an issue or a problem in your math, in your solution, because you've only got a point load here. Okay. I've got 2 or 3 other examples in these slides, and I'm not going to go through them all because we don't have time to go through all of them. But they're here and you can step through them. And for example, I'm going to skip through this, but I'll make a couple of notes about it. As you go through these slides, each slide is the next step. So there's like, I don't know, 15 slides to solve this problem. You can do it on a piece of paper almost as fast as you could read the slide. You could write this stuff down. So there's a lot of material here only because I made each slide just a single step in the process. And as I said with the last example, in this case, the problem is a simply supported beam, meaning it's free to move over here, and this is a pin, and those are rollers, and freely supported means that that can move back and forth. And this might be a problem that's applicable to automotive engineering. You know, if you want to know how big your axle should be on your car, that's what you need to do. You need to do an analysis. When you put the entire weight of the car on the axle, how much is that axle going to flex? You really need to know that, because if it flexes too much, the wheels are going to splay out, the bearings aren't going to work properly, and the car won't move properly. It's also done in structural engineering. Heck, even in electrical engineering, if you're laying out fiber optics or electrical wires, you're going to put them in a conduit, and you want to make sure that conduit doesn't flex so much that it stretches your wires. I mean, simple examples of where this kind of problem might be applicable. And if I were to tell you, you've got this beam and there's a load at the middle of the beam, and the question says, what's the maximum deflection and what's the slope at x equals 0? And we can use derivatives to solve this. In order to determine the maximum deflection, you need to know, where does that occur? Where does that point of maximum deflection occur? Where do you think it's going to occur? Right in the middle, right? I mean, that would be intuitive. If you think about it, if you were to stretch a piece of wood across these two tables and stand on that piece of wood, where is the maximum amount of sag going to be? Right where you're standing, in the middle, right? So we can go through the derivatives in the calculus to prove that that's true. But if you know what you, how can I say this? If you use your intuition, when you get to that final answer, if it doesn't match your intuition, you should go back and check. Either your intuition is wrong or you made a math error someplace. So I'm going to skip through this because I want to go to another example that I think is a little bit different from, this is fairly similar to the last problem we went through. But again, in order to find the maximum, you've got the maximum deflection, you need to know where it's located, because this equation defines deflection. So you need to know what the value of x is, where y is going to be a maximum. And we can use derivatives to do that, because the location where y is a maximum is a point where the derivative is equal to 0, because this is going to be a curve, and you've got a negative slope changing over to a positive slope, so you've got to have a 0 slope in there. And so you can use that to locate your maximum. All right. So again, you can go through these. Each slide is the next step in the solution. Figure out where y max is located. And here again, let me just come back to here. When you take this derivative, you end up with the value of x can be plus L over 2 or minus L over 2. So what do you think the value of x is really going to be? Because it can only be one. It can't be both. So are you going to choose positive L over 2 or negative L over 2? Positive. Why? Well, it is easier to work with, but there's a more physical reason for it. This is x equals 0. This is x equals L over 2. Where's x equals minus L over 2? Over here. Right. It's not on the beam. Right. So that cannot be your answer. It's not physically possible. So again, use of intuition is a really useful tool that will save you a lot of time and energy. All right. So We figure out where the maximum is located. It's located at L over 2. Plug that into the original deflection equation here and find what the value of L over 2 is. And when we go through that and do the math, and this is all algebra at this point, minus PL cubed over 48 EI. All right. So then the next question was, what's the slope at x equals 0? Well, the slope is the derivative of y over x. And we take that derivative, and with the derivative, we put a value of x equals 0 into the equation for derivative, and we find out that the slope at the origin is PL squared minus PL squared over 16 EI. So I wanted to come to this equation because it deals with trigonometric functions. And it also deals with a distributed load as opposed to a point load. So in this case, again, it's simply supported beam, meaning those ends can flex, and the end that's got the rollers can move back and forth as needed. And we're given two equations. One is for the deflection, y over x, or y of x. The deflection is a function of the sine curve. And when you look at the distributed load, which is given as some initial value of load times a sine function, intuitively, it makes sense. This looks like half of a sine curve, right? You could take this and continue it on, and you would get your full sine curve. So we have a formula for our distributed load in the upper part of the slide. W naught equals, or times sine of pi x over L. And then we have another formula for the deflection. W naught L to the fourth over pi to the fourth EI with a negative sign in front times sine of pi x over L. And the question is, what's the slope, the moment, and the shear force? So this is simply the first, the second, and the third derivative of this equation. So the slope is the first derivative, and we need to take the derivative of this. This is, in fact, a constant times the sine of a constant times x. And I just showed you, if you want, you can go through and figure out what the derivative of the sine is, and it's the cosine. If you look in the back of the textbook in the rules, what it tells you is that the sine of a constant times x is equal to the constant times the cosine of the constant times x. And the derivative of a constant times the sine function is equal to the constant times the cosine function. Does that make sense? So you guys know where the table is in the back of the book, right? You've seen that? Okay, you're using it? All right. So we take the derivative of this equation. And basically this slide tells you what I just said. WL to the fourth over pi to the fourth EI is a constant. So if you take the derivative of a constant times a function, that's the same as saying a constant times the derivative of a function. So we can just pull that out. And the derivative of the sine of a constant times x is equal to that constant times the cosine of the parenthetical. So the derivative of this equation is equal to that constant, W naught L4 over pi 4 EI, times the derivative of the sine, which is pi over L cosine pi over Lx. And again, the rules for differentials are your best friend in this case. If you have to sit down and write out and resolve that and prove that the derivative of the sine is the cosine, is going to take you a long time. So this is the equation for the slope, fairly straightforward. And the next couple slides are really what I showed you on the board. The derivative is the slope of the tangent line, and that's how we know the derivative of the sine is equal to the cosine. And this is just a graph I pulled from the internet. Here's your sine curve in red. And if you look at, again, the slope at this point, at the 0 point, the slope of the line is very large and it's positive. Where the sine curve plateaus, the slope is 0. And so the cosine, or we can plot the slope at 0, and we can go through the process. And when we look at this blue curve, it's a cosine curve. And that's how we know that the derivative of the sine is the cosine. All right, so we're back to the slope. We move on to the moment. The moment is simply the second derivative. We just took the derivative of this. So now we can take the derivative of the slope and determine the moment. So in this case, what's the derivative of the slope? The derivative of the slope, here's the slope. W naught L cubed over pi cubed EI times cosine pi x over L. Again, W naught L cubed over pi cubed EI is a constant. So we can pull that out of the derivative. And we then only need the derivative of cosine pi x over L. You can go through the same process and derive that derivative. Plot the cosine. Yes? Can you speak up?
Do you take the derivative of one term and then you take the derivative of cosine and constant?
Well, in this case, no. In this case, and in any case where it's a constant times a function, and you're going to take the derivative of a constant times a function. You just pull the constant out of the derivative. You take and you multiply the constant times the derivative of the function. So let me do it. Let me write it on the board. Oh, well, let me go back. I'll show you. Here. So the derivative of displacement is equal to minus W naught L to the fourth over pi to the fourth EI times pi over L. So L to the fourth becomes L cubed and pi to the fourth becomes pi cubed. So this fraction W naught L cubed over pi cubed EI is a constant. That gets pulled out. The derivative of the cosine is minus the sine. And again, you can, if you plot the cosine and then plot the slope at the key points, what you'll find is the inverse of the sine curve. And we simply take this coefficient out. We multiply it. So the cosine of a constant times, the derivative of a cosine of a constant times x is equal to that constant times minus the sine of the constant times x. We make this substitution to get the moment. So we have our constant, W naught L cubed over pi cubed EI, and the derivative of the cosine omega x, in this case omega is pi over L, so the derivative of this is simply minus omega, which is minus pi over L, times the sine of omega x, sine of pi over L times x. And when you simplify all of that, the moment is W naught L squared over pi squared times the sine function. It was canceled. Because remember, if we go back last time, the moment is defined as EI times the second derivative. Excuse me. And when you take the second derivative, you end up with EI in the denominator. You have EI in EI times 1 over EI. It cancels. Excuse me. Oh. All right. So this question says, what is the slope, what is the moment, what is the shear force? Well, the slope is the first derivative. The moment is the second. And the shear force is the third. So this is just showing you how the derivative of minus the sine is equal to the If y is cosine, the derivative of y is minus the sine. So you can sort of go through this process of determining the slope at each of these points and seeing how that cosine curve is developed. Are we on board here? Am I going okay? Is this like completely beyond you? You don't really understand it? Perfect speed? Going way too slow? Not really sure. You don't know enough to ask questions. Well, you know, there is a great theory of education that says you start at a point where you got no idea what anyone's talking about. And then you get to the point where you understand what somebody's telling you, but you have no idea how to do it. And then you get to the point where you did it, but you have no idea how, and you can't do it again. And then you get to the point where you've done it, and you can do it again, and you know it. So, are you guys at the point where you have no idea what I'm talking about?
Yeah, I'm at that point.
You're at that point, okay. So, the last time I taught this class, there was a lot of discussion about how do we know that the derivative of the cosine is minus the sine? Right? So my short answer was, because that's what the table in the back of the book tells you. Right?
So it's something you have to know by heart?
Well, that's the easy way. And I would say that you don't know it by heart. I would say that you use it often enough that you just remember it, right? Think about it this way. Do you know how to tie your shoes by heart, or do you just do it? You just do it, because you do it every day. Well, when you get into calculus and you get into other engineering courses, you'll be doing this stuff so often, you won't even think about it. You'll just know it. It's not a memorization, you just know it. So that's the short answer. The long answer is, the definition of a derivative is the slope of the curve. So if you want the derivative of the cosine, determine the slope of the cosine at various points. And when you plot up that curve, it turns out to be, in this case, minus the sine curve. So you can derive it. And when you get into some of the calc courses, they may actually ask you to prove this. For us in this class, I simply want you to be able to know where to find that information. And that's in that appendix. And when you take your exam, you've got that cheat sheet, and that should probably be something you're going to write on your cheat sheet.
Do you know when the exam is?
I don't know. Is it not on the syllabus? Okay. Yeah, so like next week? Okay.
It's a nightmare, isn't it?
I think it's the first week of April.
Okay. Well, the definition of the moment is EI times the second derivative of displacement. That's the definition. So that's how I know to take it out. Over here, we're trying to take the derivative of this whole function. And if this were, for example, if this were W naught L cubed times x over pi cubed EI plus x squared times the cosine, I couldn't take that out, right? Because there's an x in there that's going to vary with the derivative. But in this case, each value in this first fraction is a constant. The length of the beam is a constant, the flexural rigidity is a constant, pi is a constant, and this maximum load is a constant. So if they're all a constant, the derivative of a constant is by definition a constant. You just pull it out, so you don't have to deal with it. Is that?
Yeah.
Okay.
Pretty much like y of x is given, and we just gotta know if it's sine of x.
Yeah, I mean, in this example, you're given the displacement. Say that again?
I'd like the degree if it's like the fourth, the third, and the second.
Yeah, now I don't know, to be honest, I don't know how many problems like in your homework you've had where you had to take the second or third derivative. The first two, okay. So there's really no complexity to doing that other than You're right. You're just taking derivatives, and you just have to remember which equation you're using, I guess. So you start with this one, take the derivative of that to get slope, take the derivative of slope to get moment, take the derivative of moment. Did I write that? Oh, I haven't gotten to that part yet. To get shear force. Yeah. Okay. Okay. All right, so I'm going to talk about shear force. Again, shear force is simply the derivative of moment. And the derivative of moment is EI times the third derivative of displacement, because EI is a constant. So you can pull that out. So the third derivative, this is the second derivative, W naught L squared over pi squared times the sine. Take the derivative of that. The derivative of sine is cosine. So we're going to take EI times this constant times omega, in this case is pi over L, times the cosine of omega x.
That gives the shear force?
And that will give us the shear force. So this is a constant. You pull it out. The derivative of sine omega x is equal to omega times cosine omega x. And in this case, omega is pi over L. So pi over L, the pi over pi squared becomes pi. L squared over L becomes L. So we just simplified it right there. Okay. So simply taking a series of derivatives, you get the slope, the moment, the shear force. The fourth derivative is the distributed load, and this is how you can check your answer, because you were given the distributed load to begin with. So the derivative of this should be the distributed load up here.
Once you get the derivative, cos is going to be sin. And then this one, wait, how do you factor out the WOL over pi?
Well, what's the derivative of cosine?
Sin. I mean,
What's the derivative of cosine, the cosine of omega x?
you just said that.
Right, so it's omega times the sine of omega x. All right. You know what, though? Why do I feel like I dropped a negative sign somewhere? Did I drop because... Oh, well, except we started with negative. So we have a negative times a negative, so that gets dropped. So this should be positive, right? So the moment is correct. And then the derivative of sine is cosine. Right. So let's take the fourth derivative. If we do that, I know why. I know what happened. The distributed load is minus EI times the fourth derivative. That's where I was looking for that minus sign, and that's where it comes in. So the derivative of the shear force, the negative derivative of the shear force, is your distributed load, which makes sense if you think about it, because the distributed load is pointing down. It has to be negative because the shear force is pointing in the opposite direction of the load. So if we take the derivative of our shear force minus the derivative of W naught L over pi times cosine pi over Lx, the derivative of cosine omega x is minus sine omega x, and then the two negative signs cancel and we end up with our distributed load. So again, there's a way of checking your answer. And it's imperative that you check your answers, because especially when, later in your academic career, you're going to find places where you have to make a guess in order just to get started. You can't even begin to solve the problem unless you guess at the value of some parameter. And if you do that, you go through your whole process, the whole calculation, and you come up with a number, then you've got to make sure that that answer makes sense given your first guess, or that your first guess still makes sense, and you might have to go back and solve the problem several times. But in this case, you get to do that. All right. So with that, there's a couple of other examples in here that I'm going to let you guys look through on your own. This example is fairly interesting. If you think about any kind of construction, all kinds of mechanical and structural situations, you will have a beam or some other material that is being stretched. And you can imagine concrete, for example, is very strong in compression, not so much in tension. Steel is fairly strong in tension. And so you might want to do an analysis of how's that thing going to break if you put too much pressure on it. Yes? Okay. Say that again?
Did you factor it out when we did the third? No, that's a constant. Right? We didn't go away with the derivative. Yeah. When we took the third derivative, we took the fourth derivative, did it go away? No, when we took the third derivative. Well.
Yeah. I'm just going back to the beginning to just to find out what happened there. Because in the original problem, if we go back to the original problem, we have EI in the numerator for the deflection. We take the derivative for the slope, and we still have EI in the numerator. Let's skip through this. We go to the moment. Now we take EI times that derivative, and this is where the EI gets dropped out. Because it's in both the numerator and the denominator. So we don't have it in the moment. We take the derivative, we take the shear force. The shear force is EI times the third derivative of y, which is the derivative of the moment. Well, we already figured out what the moment was. And the value of EI canceled in our expression for moment. So there is no EI here. And then, right, so here, EI times the third derivative of y, which is equal to the derivative of the moment. Well, there's no EI in the moment, so there's no EI here. We come down to the distributed load. It's minus EI times the fourth derivative. Minus EI times the fourth derivative is equal to minus the derivative of the shear force. And the shear force is given here. There's no EI in the shear force. So the derivative of the shear force is equal to minus EI times the fourth derivative of y. We've already gone through all of this and determined what that is, and that's what we're taking the derivative of, not this. If you wanted to start with this equation and take the fourth derivative and then multiply it times minus EI, you would end up with, whoops, this here.
So if you take the derivative, right, and say you did it fine, negative dv and dx, you would do negative 3i times the derivative of y.
Well, I'm not sure. Say that question again.
Because we found the third derivative of shear force, so we only have to take the shear force, like the derivative of shear force once again for the fourth.
Yes.
But if we didn't find the third derivative, could we just say negative EI times the derivative of y of x?
The fourth derivative of y of x.
Fourth derivative.
Right. So Right, so if you start with this and take the first and then the second and then the third and then the fourth derivative of y of x and multiply it times minus EI, that's correct. That's correct. And you're going to end up with that. Yeah. All right.
I got a question.
Okay.
So you get like when you get the fourth derivative, right? Or just the fourth derivative, and that's all they give you. Can you work your way back to get that?
If you're given this,
Yeah.
can you work your way back to get what?
The shear, not the shear, the
Right, this is the
pounds and inches, the weight.
way back here?
Yeah.
Absolutely. Yep. And we're going to talk about that. That's called integration.
All right.
Yep. Yep. Integrals are just the opposite of derivatives. And as
It sounds easy.
um,
But it's not. I've been trying to deal with the homework and it's really, I've been staring at the same problem for like 4 days.
well, there are some rules that make it easy. And integrals are one of those things. Did you guys ever play backgammon?
No.
No. Okay. Did you ever play chess?
Yeah.
Okay. Did you ever see like 6-year-olds playing chess? Right? I mean, they understand the rook can move this way, and the king can move this way, and the bishop can move this way, and the knight can move. Right? They understand sort of the basics. They don't know the game, but they can sit there and play the game. Right? So integrals are sort of like that. When you start out, you know that you figure out what the rules are, and you can do it. But there are these people called theoretical mathematicians who are the equivalent of grandmasters in chess. Right? They're like orders of magnitude beyond normal human beings in their capabilities of doing this kind of stuff. You learn how to do it, and then the more you use it, the more you learn how to do. And there's always going to be, there's a point where you get to that you can't take an integral. You can't take the derivative. It's not possible because the equation is too complex. At that point, you plug in some numbers and you try to solve it numerically. But that's like grad school level stuff. So integrals, what you guys are dealing with, what we're introducing you to here is just getting used to some of the rules and playing with the numbers and the terminology and that sort of thing. And sort of understanding why you're going to need to use these as you get deeper into your subject matter. Okay, anything else? So again, I'm going to skip through this, but it's going to do you well if you go through these slides. And in this case, again, this is what you see when you have a beam or some material and it's pulling apart. Think about a house. Like, if this were a house, there would be 2x4s in the wall back there, right? And there would be a header and a footer across the bottom of the 2x4s that are attached to these walls. And those walls are pulling on those headers and footers, right? They could be pulling them apart, and you want to make sure that that beam inside that wall is strong enough to resist that pulling. And you want to understand, if it starts to break, where is it going to break? And so this problem talks about that. The shear stress and the forces that are applied to a beam. And one of the things it goes through is the fact that if you have a beam, say this is your beam, and you put a force on it so that it's pulling this way, the beam might split in half, right? Or it might split at some angle. It might split this way. Probably not, right? So if you're pulling this, you might end up pulling the bottom and the top apart. Or you might pull them apart at some angle in there. And you don't know what that is. And so this example steps through the process to determine what that angle is going to be. It involves some free body diagrams. Essentially what it says is, you put a force on this beam pulling that way, that's a vector. That means it has a magnitude and a direction. Anything with a magnitude and a direction can be resolved into a perpendicular force and a parallel force. So if the force is coming this direction and this beam splits at some angle, there'll be a force pulling perpendicular to that face and a force pulling parallel to that face. And if this is the magnitude of the force, then perpendicular, the force is equal to that magnitude times the cosine of the angle, and the parallel force has a magnitude of the force magnitude times the sine of the angle. So you can go through this, and there's a lot of trigonometry in here, and a fair amount of algebra before you ever get to the calculus. And when we get to the calculus, let me come up to here. So at this point, we've got two shear stresses, one perpendicular to the face, one parallel to the face, both expressed as functions, trigonometric functions. One is a cosine squared function, one is a sine cosine function. And the reason I want to sort of leave this in here so that you can go through it is because taking those derivatives is where you use the product rule for derivatives. And the product rule says if you've got function x times function y, the derivative of that is function x times the derivative of function y plus function y times the derivative of function x. All right? So you guys all have your books? Open up to the back of your books. I want to show this to you. So this is like just 1 or 2 pages in. At the top of the page it says differentiation rules and integration rules. Very back of the book. Looks like that. All right. So you see where it says the first column about halfway down it says product rule. It says the derivative of f of t times g of t is equal to f of t times, and it says g dot. That's a symbol for the derivative of g of t. So it's the first function times the derivative of the second plus the derivative of the first times the second. I like to call it the first times the derivative of the second plus the second times the derivative of the first. That's what they're saying there. And that rule will help you take the derivative of the cosine squared, because cosine squared is cosine times cosine, right? So the derivative of the cosine is minus the sine, right? So cosine times cosine, derivative of the first times the second, minus the sine times the cosine. Add to that the first times the derivative of the second. The first is a cosine, the derivative of the second, derivative of the cosine is minus the sine. And I'll show you this on the slides in a couple of minutes. So we're looking at maximum angles. We know that the derivative is 0 at a max or a min, so we can figure out where these angles are. And this is where we need to take the derivative of sigma. This is sigma, which is the derivative of cosine squared. Cosine times cosine. It's the derivative of the first. It's the first times the derivative of the second plus the second times the derivative of the first. The derivative of cosine is minus sine, and if it's cosine times cosine, the derivative of that, let's write this out. The derivative of the first is minus sine, and we're going to multiply that times the cosine, plus the second times the derivative of the first is minus sine. We'll just put some parentheses in there to help make it clearer. So what do we end up with? Minus sine cosine plus minus sine cosine. Minus 2 sine cosine. So that's where this comes from. And similarly, if we're going to take the derivative of sine times cosine, you guys have this? I'm going to erase it. derivative of sine times cosine, we'll take the derivative of the first is the cosine times the second, plus the second, I'm sorry, wait a minute, what did I do here? Let's do it this way. The first times the derivative of the second, plus the second times the derivative of the first. So that's sine squared theta plus cosine squared theta. Right? I can't hear you. Oh. Is that right?
Would that be sine times negative sine?
It's the first times the, thank you. Yep. And then the second times the derivative of the first. So it would be minus sine squared plus cosine squared. Yes. Good catch. So you're going to have to go through these slides on your own because we just, you know, we're going to run out of time, and I want to touch on integrals so that we can talk about those a little bit next week as well. And I'm not sure how useful it is to go through 2, 3, 4 examples of this stuff in class. I think with the slides and your homework, I think that's the best thing you can do. There's nothing you can do that's better than practice. Do the homework, go through that. Can you put your phone away? You just shut it off and put it away. Because I have to tell you, if you're not paying attention, you might as well leave. I'm sorry. I'm here. Excuse me. I'm speaking. As the instructor, my rules are no phones. So the example is here. Pay attention to the derivatives that are used and why they're used. Certainly, if you have an issue, if you're confused by anything on the slides, you've got my email. You know where I am. Let me know. But I think that these highlight the issues that I wanted to in terms of some of the derivatives that we wanted to go through. Okay? All right. Say it again? Yeah, I was going to do an introduction to integrals, and then next week talk about applications in statics and dynamics. So integration is the opposite of differentiation. So when we talk about the derivative of the sine is the cosine, the integral of the cosine is the sine. And I'm going to go through this example, and I believe that this is in your textbook. And I'm going to go through this, and let's just go through this example to show why integration is important and what it can do for you.
It's not the same slide pad?
No. So this is it's on Blackboard. It's in, but it's under the Chapter 9 stuff. In this case, and this is supposedly a true story, there was somebody who was working as an engineering co-op, was working for a company called DAP. Yes? What other two homeworks?
It says, for homework after today is, chapter 8, questions 8, 9, 10, 21, 23, and 24. But for tonight, the one that's due today is 1, 4, 6, 14, and 17, all chapter 8. And then even after that, we have another one on chapter 8 for 25, 26, 27, 28, 30, and 31. So we
Wait a minute.
Right, that's what I'm saying. So we got
Today's the 23rd.
right. So and we have to do chapter 8 to 26 apparently. And then like we jumped to chapter.
Okay,
9.
this is, can you go back to Blackboard? This syllabus is off by a week from the one I was given. So let me just double check.
Is that the updated one that you sent us?
It might be.
No, the updated one isn't on Blackboard. It just emailed it to us.
Oh,
But the updated one I have is still,
I got the updated one right here.
it's still what?
still 3, like it's still 8.
Right, well, so the original syllabus, I was only going to be here last week, this week, and next week. But according to the syllabus that you're showing me, last week was supposed to be somebody else, and then I'm going to be here for the next 3 weeks. So I think Dr. Sadigapour changed the syllabus but didn't tell us instructors. So I might be here for an extra week, which is, I mean, I'm okay with it, because if that's true, I'll spend the time talking about some more time on differentiation. I thought I only had another week here to cover this material. Right, so this says I should have been here, that I was going to cover this material on the 16th, the 23rd, and the 30th, and that's the syllabus I'm going by.
Yeah, but the new one says, yeah, this is the old and new one.
Yeah, so when did you guys get the new one? When did you get a new one?
I don't know, I can't remember. We got it in an email. This is the old one.
Wait a minute, what's the old one?
This one. See?
No, this is the new one.
No, that's the old one.
This is the old one?
Yeah.
This is
that's
the new one. Oh, okay, so this is the one I'm working off of.
Yeah.
Right, so your exam is April 6th.
The first week of April.
Um,
And here the exam says April 13th, so that's the new one.
Okay. Right, so I'm right. So my concern is your syllabus says you're supposed to look at integrals today and then have homework.
This was the homework due today. And
Which
this is
one?
This one.
That was due today.
That's due in the recitation after this.
So your homework is a couple of lectures behind. Right? Because this says March 16th homework is here.
Is this Matrix? This?
No, this is chapter 8. This is
the Matrix?
This is the Matrix.
Or you're
This is the derivative.
you're a couple of weeks ahead of the lectures is what's going on your
Yeah.
homework. Yeah. But the lectures at this point, today's the 23rd, and so I'm at least a half a lecture behind because I haven't even started integrals yet. And that's what I was trying to get started on, was the integrals.
So then, what, like, so the integrals are still part of chapter 8, or is
No. Integrals go into chapter 9. That's chapter 9. Yeah, so what I'm going to talk about next would be applicable to this homework assignment.
Well, I guess I gotta talk to the TA and we'll go.
Yeah, so because which one are we supposed to follow?
Yeah,
This one
because
or-
no, we follow this one, but I'm saying for the homework, we wouldn't know, like, we'll be behind because we'll still
yeah.
be doing
But-
derivatives.
Right, but you should, based on these slides and these last week and this week, you should be able to do all of these problems.
Okay.
Yeah.
Okay.
Okay? So,
23rd,
It-
Then it says introduction
Right.
to
The first part of
Because I did this one. This is what I did last night. 1, 4, 6, 14, 15, and 17. Was I supposed to do 8, 9, 10, 21, 23? And I'm late on,
well, I don't know, these folks over here are still, you guys are still working on chapter 7 problems? Is that right?
No.
Oh, wait a minute.
right, 8.
Let me see
you
something, let me
did
see.
8, 1, 4. Yeah, that's what I did too. Okay, so if we all did the same thing, I don't think we all can be penalized.
No, that's
Okay.
Because I handed 7 last week.
Right, and I handed it 7
Okay.
last week. Right.
seven lines.
All right.
yeah, 7 was last week.
I thought it was only
Okay,
one.
so my schedule is the correct, my lecture schedule is correct, right? Okay,
Yes.
okay. Throw me off altogether.
It's all sorted out.
Okay, because that syllabus right there is on Blackboard.
Right.
That's the one that
This
I've,
one, this one's not on Blackboard. This is the email one, but I got a different one on Blackboard.
Yeah, there's a different one on Blackboard.
There's a different one on Blackboard. I
You
got
said that that one was outdated.
okay.
Yeah.
Yeah, because he messed up.
think
It was,
that's
it was a
what
week
it
missing.
is.
Yeah, it was a week missing.
Yeah,
And then we had to
the
drop the
exam
homework
was-
down a whole week to add whatever he missed. And then I guess we didn't have homework this 1 week that they said we were supposed to have homework. So that's 2 days we pushed down. Yeah, so we pushed the homework down 2 days. Okay. Okay. So tomorrow.
So this is chapter 9.
This stuff is chapter 9, yeah.
So I got to do chapter 9 for homework tonight.
No.
Tonight we still do
You're-
A.
It seems like the homework is a week or two behind the lectures.
Okay, that's great.
So you're getting the lectures, and then you don't have to do this stuff for another week or two, which I don't.
I'm just not. I don't even know how to do an interview and finish 14 and 15.
Well,
All right.
this time we
So
did
I'm
the
learning
second
it.
set of problems from chapter 8.
Okay.
He said he's introducing this to us today, and he's going to go into detail on it next
So
week.
that way, by
Right.
the time I do my homework, I should be comfortable with it. Okay, makes sense.
I hope.
3 sections from chapter 8. That's
Yeah,
just
we have
confusing.
3, that's why.
Yeah, we got 3 sections
Because
to
it's not like, okay, like if you introduce it today, we do 8 is gonna be due next week, and then 9, but it's not like that. We
Right.
have 8, and then 9.
Yeah.
I
So
think-
your homework. It seems to me your homework is a week behind.
Yeah.
I mean, it's good that you don't have any chapter 9 homework due this week. But if your chapter 9 homework is not due for 2 weeks, you might be on chapter 10 by then, and you're so.
What about our exam that's coming up? Like, is it going to be on
There's
chapter?
gonna be a review with Dr. Pelopaka.
Okay.
And they will. If the past is any indication, they will adjust either the exam date or the material covered on the exam to match where you are in the lectures. And
On
this.
the next exam.
Okay.
The next exam is Pelopaka with matrices and stuff. I think you're in the third exam.
Oh,
Chapter
okay.
6, 7, and
Chapter 6, 7, and.
Also, this is the final then.
yeah, this
Yeah,
is.
this is probably the
Yeah.
final.
I don't know. We can go into this.
I don't know. Well, when is your recitations? When are you,
Mine's is today.
So mine's is
I
today.
just one tomorrow.
okay.
Mine's is today, and I got a whole lot of questions.
Right
So-
after this.
One of the questions should be, where are we supposed to be on the homework in connection to the lectures? And where's the exam going to be?
But it's always been like, he taught us, like when the dean was here, he taught us, and then we did the homework, and it was due the week after, and then he started, so it's always been like that,
Okay.
like, yeah. So it's always been like a week kind of.
Yeah.
I mean, it always
All
been
right.
we learned in the class. And we
Yeah, and then we
do
did the
it.
homework,
Yeah,
yeah, it's always been.
All right.
kind of like a basic school regurgitation. What do we force things to throat? There you go.
Okay. All right. On that note, let's talk about this. And if I have to adjust things for next week, I'll do that. I'll talk with the dean, with Dr. Sadigapour, and make sure everything's on track. So in this case, this is he was a professor who worked as an intern for a company called DAP. Have you ever heard of them? Anybody do any home construction? Caulking around doors and windows, DAP makes that, right? They make those kind of materials. And they had this factory in this warehouse, and they would have these trucks coming down the road, and they would have to turn into their warehouse. And they're big tractor trailers. And the original driveway was squared off right to the street. So, of course, these trailers would just run right through the grass and whatever. So they decided that they were going to give up on all their pretty plantings at the corner and just pave it because they were getting ruined anyway. And as an intern, as a co-op, this person was told, go out with the